Welcome to the Explainer. Today, we're going to tackle what looks like a complex chemistry problem, but really, it's a fascinating story, a story of atomic transformation.
All right, let's jump right in. What you're looking at here isn't just some complicated diagram. Think of it as a roadmap. It shows how one element literally turns into another through radioactive decay. Our job? To follow this map all the way to the end.
So, that's the big question, right? We've got this map, but there are missing pieces. Our mission, and we're in this together, is to be nuclear detectives. We're going to fill in the blanks, and in doing so, we'll start to understand the fundamental rules that run the show deep inside an atom's core.
Okay, so before we start filling in the gaps, let's skip to the end of the story. The final destination here is Cobalt-59. You can see it right there at the bottom of the chart. But why? Why does the journey just stop there?
Well, it's pretty simple, actually. This whole kind of complicated-looking chain reaction, it's all about one thing: nature trying to find balance. It's a journey towards stability. And for this particular path, Cobalt-59 is it. It's the stable, non-radioactive finish line.
All right, now that we know where we're headed, let's rewind and fill in those missing steps. We'll start with that first question mark, right at the top of the chain. Let's solve piece number 1 of our puzzle.
So the map is telling us that some mystery element decays and becomes titanium-59. The question is, what is it? To figure that out, we have to look at how it's transforming.
And the answer is scandium-59. But how do we know that? Well, you have to look at the arrow on our map. It tells us the exact type of decay happening, and in this case, it's something called beta-minus decay.
So beta-minus decay has a specific rule. A neutron inside the atom's nucleus decides to become a proton. When that happens, the atomic number, which is what defines an element, goes up by 1. So if we end up with titanium, which has 22 protons, we must have started with the element that has 21 protons. And that, my friends, is scandium.
And here's what that looks like as a complete reaction. See how the mass number, that 59 up top, stays exactly the same. But the atomic number, the little number at the bottom, clicks up from 21 to 22. Boom, first puzzle piece is in place. Let's find the next one.
Okay, on to our next mystery. We've got another blank spot on the map. This time, we're looking for the element that decays into nickel-59 on its way down to our final goal, cobalt. And just like before, the process itself is the clue.
But this time, things are a little different. We're looking at a beta-plus decay. It's basically the opposite of what we just saw. Instead of a neutron becoming a proton, here a proton turns into a neutron. That means the atomic number actually goes down by 1. So, following that logic, if we end up with nickel, which has 28 protons, the element we started with must have had 29 protons. And what element is that? It's copper. And just like that, puzzle piece number 2 is solved.
All right, so we've mapped out the entire journey to the stable Cobalt-59. Now, to really understand why stable is such a big deal, let's talk about its famous unstable cousin, Cobalt-60. You won't see it on this particular decay map, but trust me, it's a huge part of the cobalt story. This is the stuff used in everything from cancer therapy to checking for cracks in industrial pipes. So what's the big difference between the stable version and the radioactive one? You're looking at it. It's just a single neutron, that's it. They both have 27 protons. That's what makes them cobalt. But that one extra little particle in Cobalt-60 is the difference between being perfectly stable forever and being radioactive.
And there's actually a rule of thumb in nuclear chemistry that helps explain this. Nuclei just tend to be more stable when they have an even number of protons and an even number of neutrons. Cobalt-60, it has an odd number of both, 27 protons and 33 neutrons. That odd-odd combo is a huge red flag for instability in the atomic world.
Okay, so if Cobalt-60 is unstable, that means it's decaying, but how fast? Well, we measure that with something called half-life. For Cobalt-60, it takes 5.27 years for half of a sample to decay away. But what if we check in earlier, say after just 3 years? How much is left? Well, the good news is we don't have to guess. There's a formula for this. We can calculate the exact amount left using this standard half-life equation. All we have to do is plug in the numbers. Little t for the time that's passed is 3 years, and big T for the half-life is 5.27 years. You run the numbers through that formula, and what do you get? 67.4%. So after 3 years, a little more than 2/3 of your original Cobalt-60 is still there, just waiting for its turn to decay.
And that brings us to the final and, honestly, the most powerful piece of this whole puzzle, the energy. When Cobalt-60 does finally decay, it doesn't just change into another element. Something incredible gets released in the process. This is where we get into the heart of Einstein's famous E equals mc squared. A tiny, tiny bit of matter, of mass, doesn't just disappear. It gets converted into a massive amount of pure energy. This is called the mass defect. So let's see just how much energy we're talking about from this one single event.
So what scientists do is they very, very carefully add up the mass of everything before the decay, the Cobalt-60 atom, and compare it to the total mass of everything after, the new nickel-60 atom and the beta particle. And when they do, they find a tiny discrepancy. A little sliver of mass, just about 0.0024 atomic mass units, has, well, it's vanished.
So, the big question is, where did that mass go? Did it just disappear? Nope, it wasn't lost at all. It was transformed. It was converted into pure, raw energy. And the amount of energy is staggering. That tiny bit of missing mass was converted into 944 million electron volts. Now that might not sound like a lot, but for a single, microscopic atom, that is a huge release of energy. And just to be crystal clear, this energy is released. It's not put in. It's a burst of power that comes from deep inside the atom itself.
And really, that's the ultimate solution to our chemistry puzzle. We started by just following a map of decay, and we ended up uncovering the incredible forces locked inside an atom. It's this idea of immense power being released from a change in mass so small you can barely even measure it. And that is the secret of the nucleus.